Today we will be studying the edge triggered interrupt. In yesterday's class, we had studied or we had taken a general idea about what are interrupts, okay, how to program the interrupts, okay. We had seen the steps in executing the interrupts. We also saw how to enable and disable the interrupts by configuring which register? IE register, interrupt enable register, okay. So now today what we are going to see, we also saw how to program timer interrupts. We discussed about IVT also yesterday. Then we saw how to program the timer interrupts, okay, and we also took the external interrupts. Now yesterday I told you that there are two external interrupts, INT0 and INT1. The vector addresses of ISR for these interrupts are 0003H and 0013H respectively, okay. Now these interrupts can be defined as on the basis of two things. How are they triggered? Whether they are triggered on edge or they are triggered on level. So interrupts, external interrupts can be triggered on level. Level means a low level triggered interrupts. Upon reset, these two interrupts INT0 and INT1 are always defined as low level triggered interrupts. Now if we want to use them as edge triggered, edge means what? When a high to low transition, is obtained on any of these pins by connecting an external device which gives the signal, the interrupts get defined as edge triggered interrupts. Now how do we define the interrupts as edge triggered interrupts? For this, we have to configure the T-con register. So this register looks familiar, okay. We had used this register when we did the timer programming, okay. This register consists of two parts. The upper 4 bits are used for timers and the lower 4 bits are used for the interrupt section, okay. So let us see the lower 4 bits of the T-con register and try to understand these from this slide, okay. So coming to this slide, okay, this is the T-con register. As you can see, TF1, TR1, TF0, TR0 are the timer bits, timer flag, timer run control bit for timer 1 and timer 0. We are interested in these 4 bits, IE1, IT1, IE0 and IT0. Okay, so we are interested in these 4 bits, okay, IE1, IT1, IE0 and IT0. We are interested in these 4 bits. So coming back to the blackboard, okay, now these upper 4 are used for timers, okay, these are the lower 4 bits used for what? Interrupt related operation. Now this is a bit addressable register. So this is called as a T-con 0.0 bit. This is T-con 0.1, T-con 0.2. This is called as T-con 0.3 bit. Okay. Now what is the meaning of each of these bits? We'll talk about IT bits. These are called as interrupt type control bits. These are called as interrupt type control bits. So they tell us what is the type of triggering that we are going to give on external hardware interrupts INT0 and INT1. So these are only and only for INT0 and INT1. For no other interrupt these bits are used. Now upon reset, both these bits have logic 0 in them. If IT1 and IT0 are at logic 0, it means the two interrupts INT0 and INT1 are defined as level triggered interrupts. They get defined as level triggered interrupts. So upon reset, both these pins IT1 and IT0 are always in reset condition. That means level, which level? I am talking about low level triggered interrupts, okay. INT0 and INT1 get defined as low level triggered interrupts. Now if we want to configure them as edge triggered interrupts, suppose for an application we want to detect a particular signal or an interrupt on the falling or the rising edge. Then what we need to do? We need to define INT0 and INT1 as edge triggered interrupts. To define INT0 and INT1 as edge triggered interrupt, we simply need to give an instruction. SETB tcon point 0. Okay, this is for INT0. Okay, and SETB tcon point 2 for INT1. Now, if we give one of these two or both of these two as 1, then it will mean that INT0 and INT1 are defined as edge triggered interrupt. So the microcontroller will be interrupted when a falling edge will be detected on these, a high to low transition. On the falling edge, the microcontroller will be interrupted and it will be forced to go to either of these two addresses, 0003 or 0013, where the interrupt service routine for INT0 and INT1 is stored. Okay, it will go there and it will execute the ISR. Okay, so understood the use of IT1 and IT0? I hope you have understood IT1 and IT0. Now what are these bits? IE1 and IE0. Okay, so let me talk about IE1 and IE0 bits now. Okay, we have discussed IT1, IT0. Now IE1, IE0. These are called as interrupt edge flag control bits. Interrupt edge flag control bits or interrupt edge flag bits. Okay, interrupt edge flag bits. Okay, these are activated only and only if IT1 and IT0 are 1-1. If IT1 and IT0 are both 0, then for that case IE1 and IE0 are don't care. What does this mean? When IT1 IT0 are 0-0, when the interrupt is a level triggered interrupt. These two bits IE1 and IE0 are specifically for defining edge. So remember, these bits are specifically defined for defining that the interrupts INT1 and INT0 are edge triggered interrupts. That is, the microcontroller has to be interrupted when a falling edge is detected. Okay, so if IT1 and IT0 are 0-0, whatever may be the status on I1 and I0, the interrupts won't be recognized on edge. Okay, because they are already defined as level triggered interrupts. So for these two bits to take effect, IT1 and IT0 should be 1-1 or any one of them should be 1, depending upon your application. If any one of them or both of them are 1, only then the status in IE1 and IE0 will be called as a valid status. It will be called as a valid status. Okay, so if INT1 gets defined as edge triggered interrupt, okay, and INT0 gets defined as edge triggered interrupts, then in that case IE1 and IE0 will be made 1. They will be made 1. Okay, when the ISR execution is going on, IE1 IE0 will be 1-1 if IT1 IT0 is 1-1. This will remain 1 till the interrupt service routine is completely executed for INT0 and INT1. Once the ISR execution is over, what is the last instruction of ISR? It is RETI, return on interrupt. So, if INT1 or INT0 get defined as edge triggered interrupts, that is IT1 IT0 are 1-1, then first IE1 IE0 will be made 1, then this microcontroller will get interrupted. It will be interrupted, it will execute the ISR. The last instruction of ISR is RETI. Okay, so when RETI instruction is under execution, the microcontroller will make IE1 IE0 0. when the ISR execution is going on, specifically at the ending position. IE1, IE0 again will be made 0, 0. So we get a high to low transition. In high to low transition, the ISR execution takes place. Okay. So have you understood the use of IE1, IE0? Just remember, IT1, IT0 only for informing whether the interrupt is defined as level triggered or edge triggered. Level triggered, IT1, IT0, 0, 0. IT1, IT0, 0, 0, IE1, IE0 are don't care. Okay, because the interrupts are not defined as edge triggered interrupts. They are defined as level triggered interrupts. Only and only when IT1, IT0 are 1, 1, then the status in IE1 and IE0 is said to be a valid status. What status is given? IE1, IE0 are first made 1, okay, and ISR execution starts. During the ISR execution, specifically when the ISR execution is almost at the end, that is when RETI instruction is getting executed, IE1, IE0 are made 0 by the software, that is by the microcontroller. High to low. High to low transition is thus obtained on IE1 and IE0. I hope now you have understood the use of IT1, IT0, IE1 and IE0. So, this is how the interrupts function as edge triggered interrupts. Now, to understand this better, let us take an example. So, come to this slide now. The same thing is given on this slide. You can go through it. Now, read the problem statement here on this slide. What does the problem statement say? Assume that pin 3.3, P3.3 is INT1 pin. Okay, INT1 and INT0 are hardware interrupt pins. Okay, so INT1 pin is P3.3. So, assume that INT1, which is nothing but P3.3 pin, is connected to a pulse generator. So, pulse generator is going to generate pulses. Write a program in which falling edge of the pulse will send a high to P1.3. Falling edge of the pulse. It is specifically mentioned in the numerical that falling edge. That means you have to define INT1 as edge triggered interrupt. Okay. Falling edge of the pulse on P1.3. Okay. So, what does the problem statement say? Okay. Write a program. Okay. Write a program in which the falling edge of the pulse will send a high to P1.3. P1.3 is connected to an LED. It is given that P1.3 is connected to an LED. So, LED should be turned on. We should wait for some time and then LED should be turned off. Okay. That is in other words. So here what is given, which is connected to LED or a buzzer. In some cases buzzer also may be connected. In other words, the LED is turned on and off at the same rate at which the pulses are applied. So at the same rate at which the pulses are applied, the INT1 and pulses that are received, okay, the signal that is received from INT1 from a pulse generator, according to the signal received, LED is turned on and off. Okay. So, refer to the program on this slide. See the program carefully on this slide. What is the program? I have already told you yesterday. The first statement of the program is ORG0000 and LJMP main. Where is the main program? Main program is to be. So, what is the problem statement given to us? I have drawn a small figure of the problem statement. There is a pulse generator that is continuously generating pulses. These pulses are fed to the microcontroller. This is my microcontroller 8051. Okay, so these pulses are fed to microcontroller 8051. Okay, and there is an LED connected to P1.3. Now, what does our problem statement say? That as the pulse generator is sending the pulses, the LED should turn on and off according to the rate of changing of the sending of the pulses. For this, first we need to define the INT1 as a edge triggered interrupt. And this is the program for interrupts. For interrupts, we first need to configure which register? We need to enable INT1. So, we need to configure which register? IE register. So, let me draw the format of IE register, interrupt enable register, which we had seen already yesterday. Enable all Nothing over here. Enable timer 2, enable serial communication interrupt. Then you have enable timer 1, enable external interrupt 1, enable timer 0 and enable external interrupt 0. Okay. This is what is the format of IE register. So we have to configure IE register. Okay. Enable. So enable all has to be made 1 where pulse generator is connected at INT 1. So INT 1 is nothing but EX1. Enable that. Remaining bit should be 0. So what is this number? 8 and 4. So we have to configure IE register with the value 84H. So how do we start with the program? So org 0000H LJMP main. Okay. Our main program should start from which address? Yesterday itself we have discussed. The main program should start from the address 0030. So I give org 0030H. Here my main program starts. What I have to do in my main program? First step, I have to configure which register? IE register. So what I'll do? I'll give. But before configuring IE, I also need to tell that INT1 is defined as edge triggered interrupt. Now how will you define INT1 as edge triggered? I just rub this part. You have to configure the TCON register. TCON register also we have seen. Okay. TCON register. In the TCON register, TCON point 2 corresponds to IT1. IT1 is interrupt INT1 type control bit. We have to keep this one to indicate edge triggering. So I will not draw the format of TCON now. I will just tell you that TCON point 2 is IT1 which has to be made 1 so as to define INT1 as edge triggered. Because upon reset INT1 and INT0 are what? They are level triggered interrupts. This much is sufficient before we start with the program. So I give a org again here. org 0000H and an LJMP main. What I do in the main program? I start my main program from 30 org 0030H and what I do in the main program? I first define INT1 as edge triggered interrupt. So I give SETB TCON point 2. What will this do? This will define INT1 as edge triggered. Next what you have to do? Configure IE register. We have already taken the value of IE. IE comes as 84. So I give 84H and what else I have to do? Nothing. In the main program what I have to do? Only I have to inform that INT1 is defined as edge triggered and we are doing programming using interrupt. So enable INT1. Okay, so these two things we have to do. And then here I will give SJMP here at the same instruction followed by end. This is my main program. Now, where will my subprogram start? My subprogram will start at which address? INT1 ISR address starts from 0013. So I will give a ORG here 0013H. Starting ISR address for INT1. Okay, so ORG 0013H I will give. And now what I have to do? It is connected to LED. LED is turned on. Whenever a pulse is sent, LED is turned on. So I will turn on the LED. ACTB P1.3. What does this do? Turn on LED. My LED will be turned on. ACTB P1.3. Then we have to wait for some time because high, delay, low, delay and so on. Okay. So what I will do? I will wait for some time. For that I use any register. Suppose I use R1. I configure it with some random value. Maybe say 255. This is a random value. And I give a DJNZ R1 L1 at the same instruction. This is just to make the LED on and let it remain on for some amount of time. So let it remain on and then what I have to do? I have to clear T1.3, turn off LED. So LED has to be turned on. Wait, LED has to be turned off. And then RETI. So whenever there is a high to low transition on INT1 pin, the microcontroller will be interrupted. It will go to the address 13H. Here it will turn on the LED. Wait for some time, turn off the LED and come back to the main program. Okay, this is how, or this is a classic example to tell you the use of external interrupts as edge triggered interrupts. Similar programs are there in the book. You can go through the other programs from the book. So this much is sufficient for as one example for edge triggered interrupts. Now coming to the slide over here. Okay, just like sampling of level triggered interrupts we have seen, in the same way we will see a little bit of theory about sampling of edge triggered interrupts too. Now edge triggered interrupts, okay, the external source must be held high for at least one machine cycle. See the diagram over here. For one machine cycle, if the crystal frequency is 11.0592 MHz, one machine cycle comprises of 1.085 microseconds. Okay. The falling edge of pins INT0 and INT1 are latched. The 8051 are held TCON 0.1 and TCON 0.0 bits of TCON register. In short, what we have to do whenever we do sampling of edge triggered interrupts, for one machine cycle it should be high, for another machine cycle it should be low. Read the content here. Minimum pulse duration to detect edge on INT pins. To detect the edge, high to low edge, we must have high pulse for 1.085 microseconds and low for 1.085 microseconds. That is one machine cycle time. In level triggered interrupts, we had seen that the level should remain low for 4 machine cycles. I hope you remember yesterday's lecture. Okay. In yesterday's lecture, I had told you for sampling the level triggered interrupt, we require 4 machine cycles. For sampling edge triggered interrupt, 2 machine cycles. 1 machine cycle high, 1 machine cycle low. This is what you should remember when you remember the sampling of edge triggered interrupts. Okay. Now these are some of the things that we should always remember regarding IT0 and IT1 bits in the TCON register. These are the 2 points. We'll quickly go through the points from this slide. When ISR are finished, that is upon execution of RETI, the bits TCON 0.1 and TCON 0.3 are IE1 and IE0 bits are cleared. I told you this already. They become clear when RETI is under execution, indicating that the interrupt is finished and 8051 is ready to respond to another interrupt. So during the time when the interrupt routine is being served, there should not be interrupt within interrupt. So we keep them always at high. RETI clears the corresponding bit in TCON register, TCON 0.1 and TCON 0.3, that is IE1 and IE0. There is no need for instruction like clear TCON 0.1 and clear TCON 0.3. We need not do it. Okay, that's not required. So this much you should know about IT's external interrupts when they are edge triggered. Now there is a very basic question. What is the difference between return and return on interrupt? Now they both look similar. Okay, what is RETI and RET? We know the function of RET. What happens when RET is executed? The control goes back to the place where it had left the execution in the main program. Same function is performed by RETI also. RETI, upon execution of RETI, what happens? The control goes from the interrupt service subroutine to the main function again. But in addition to doing that is popping out the PC contents, the RETI also does one more thing. It makes IE0 and IE1 equal to 0. It makes IE0, IE1 equal to 0. Okay. So this is the main difference between RETI and RET. If you are asked a question about this, this is the expected answer. Here we finish with external interrupts defined as edge triggered. Next we move on to serial communication interrupt. We will see another type of interrupt that is serial communication interrupt. Okay. Now we know the basics of serial communication. We know that whenever we do any serial communication programming, we need to configure which registers? We need to configure SCON register, right? To tell serial communication mode 1 with 8-bit data, 1 start bit, 1 stop bit. We also need to configure timer register, tmod. Okay. Then we need to put the value in th register because we are using always timer in mode 2. So we are using timer 1 in mode 2 for serial communication. So we need to configure tmod register accordingly. Then what we do? We configure th register. Now what we put in th1 register? We put a value corresponding to the baud rate given in the program. Okay, and we start the timer. After this, in the regular serial communication programming, we were monitoring RI and TI flags and we were making the microcontroller wait. Okay, now this wastage of time is prevented by using serial communication interrupt. Before starting with serial communication interrupt, let us quickly revise the use of RI and TI flags. What is the use of TI flag? TI flag is used, it is reset upon before starting the transmission. TI is what? Transmit interrupt flag. Okay. So when one byte is transmitted completely, we know that the byte to be transmitted is to be loaded in which register? SBUF register. So the byte is loaded in SBUF, that is to be transmitted, and then what happens? The byte starts getting transmitted bit by bit. Okay, till the time the byte is transmitted, the TI flag remains 0. Once the complete byte is transmitted, the TI flag is made 1, indicating 1 byte is transmitted. 8051 is ready for transmitting the next byte. Okay. Similarly, RI flag. Whenever 8051 acts as a receiver, we know the use of RI flag. RI also is 0 initially. When 8051 receives the data bit by bit, it is deframed and stored in which register again? SBUF register, right? So, when 1 byte is completely received, RI flag is set, indicating that 1 byte is received. It should be picked up and saved at a particular place before losing the data. Now, keeping all this track in mind, let us see how serial communication interrupt works. Now, though there are 2 flags in serial communication, one for transmit and one for receive, still we have only one interrupt for serial communication. Okay, the TI and the RI flag bits both have to be checked. Okay, the TI and RI flag bits both have to be checked to understand which of them has invoked the interrupt. And what will be the ISR address? The ISR address will be 0023H. So whenever we are writing a program in which there is a serial communication that has to take place along with some other function, we do using the interrupt method. So what we do, we check both these flags because there is only one interrupt for both transmitting as well as receiving. So we need to check both these flags and we need to know which of them caused the interrupt. Once we know that which of them has caused the interrupt, we can then program accordingly. So this much knowledge you should have before we start with the program. Let's take a simple example of serial communication interrupt. Now we have to program the 8051. Okay. Let us write a program 8051 to read data from port 1. So, read data from port 1. Read data from port 1. Write a program to read data from port 1. Send it to port 2. Okay. Send it to port 2. This is the first task that the microcontroller has to do. Also give a copy of the data to serial communication port. So, give copy to serial communication port. Give a copy to serial communication port. Okay. Serial communication port. Okay. So that it can be transferred. Now the data has to be transferred serially. That is, transmit data serially, say at 9600 baud. Let us consider the problem as 9600 baud. This is what you are expected to do. Do 2 tasks. 1, take data from port 1, send it to port 2. When you are sending it to port 2, you also have to give a copy of it to the serial communication port. That means you have to load in SBUF register. Serial communication port, we want to transmit it serially, so we must load in SBUF. Okay, and then transmit it serially at how much? What is the baud rate given? The baud rate given is 9600 baud. So these are the two things that we have to do. So let us start with the program now. The assembly language program. Before we do the program, we have to configure different registers. For serial communication, SCON register, which will be loaded with the value 50H. Okay, TMOD register, timer 1, mode 2, 20H. TH1 register will be loaded with a value corresponding to baud rate 9600. The value is FDH for 9600 baud. The value is FDH. So we will load TH with FDH. Also we need to configure which register? We also need to start the timer. So we have to configure TCON. So that will do only SCTB TR1. Then what we have to do? We have to configure the most important register, that is IE. Okay. So let me draw the format of IE once again over here. Okay. We have EA, enable all, ET2, not used. Okay. ES, this is our bit of interest. ET1, EX1, ET0 and EX0. Which bit we want to configure? It's the serial communication interrupt problem. So we have to make serial communication interrupt 1. Enable all also has to be made 1. The rest of the bits will be 0. So you have to load IE with what value? With the value 90H. 9090. This much you have to do before writing down the program. Okay. What you have to do? SCON 50, TMOD 20. TH1 FD, that is corresponding to 9600 baud, IE with the value 90, telling us that enable serial communication interrupt. This much we have to do before starting the program. Now we will start writing the program. For the program, all the prerequisites we have already written. Now let us start with the program directly. Okay, so I will give org 0000H and LJMP main. This is what we do always. Okay. This is what we do always. Now what I do in the main program? Main I will always start from what? From the address 0030H. Okay, I will start my main program. What I have to do in the main program? I have to first send data from port 1 to port 2. That means I have to define port 1 as input. So I will give move P1, hash 0FFH. When I do this, I define port 1 as input port. Define port 1 as input port. So I give move P1, 0FFH. Then what I have to do? All the things related to serial communication. Move SCON, hash 50H. Move TMOD, hash 20H. Move TH1 corresponding to baud rate, put a value FDH. This is for 9600 baud. Okay. This is the prerequisite that we need to do, and we need to configure which register? IE register. We have already found out the value. It is 90H. So move IE, hash 90H. Okay, and start the timer. Once the timer is started, okay, the data transmission or reception, whatever has to be done, will be started automatically. Now till the time the flag is raised and all, what we have to do? Send the data from port 1 to port 2, from port 2 to serial communication port. So what I do? Move the data from port 1 to accumulator. From accumulator I have to send to serial communication port. So what I do? I put in SBUF register. SBUF, A. Transfer to serial communication port. Also give a copy from accumulator to port 2. And this you have to do continuously. So I give SJMP back. And where will my back label go? Over here. over here. Okay. So what I have to do? I have to take the data from port 1, send it to port 2 via accumulator I am sending. Also give a copy to SBUF register, because it is mentioned in the problem statement that give a copy of the data from port 1 to serial communication port. So serial communication port, how will you send the data? By putting it into SBUF register. This is my main program. Now my subprogram is given only 8 locations, 23 to 2F. That much is not sufficient for me. So what I do in this subprogram, I give ORG starts from 0023H, right? Okay, ORG 0023H, and I give a LJMP serial. I give a LJMP serial over here. So I write down my serial communication program not from this space but into some other ROM space. Hope you have understood up till here. Now let's complete the remaining part of the program. Now what is remaining? Only the serial communication interrupt program that we are supposed to write. Okay, what we are going to do in this program? Okay, I'll put any address, take any random address. Suppose I take ORG 100H, any random on chip address. Okay, and I start with my serial program. Now what I am supposed to do in the serial program? Okay, I am supposed to check transmit interrupt flag as well as receive flag. So what I do, I give any one of them. JB, jump if bit, transmit interrupt flag, suppose next. If TR flag is raised, means 8051 is working as a transmitter. So what I need to do? I need to come here, next, and what I need to do? TR flag is raised means clear TI. Clear TI, 8051 is working as a transmitter. Okay, clear TI and return followed by end. This means 8051 is working as a transmitter. If this TI flag is 0, 8051 is not working as a transmitter, we presume that it is working as a receiver. Now this is a bit contradictory, but this is what we have to assume whenever we do serial communication programming. Okay, so this means 8051 is working as a receiver. When 8051 works as a receiver, what we need to do? We need to put the value already received in SBUF into a safe place. So move A, SBUF. Okay, and I put it at port 2. Send it to port 2. I have to put at some port. I send it to port 2. And I clear the RI flag now. Okay, and I give RETI followed by end. Okay, I give RETI over here. Okay, so either 8051 is working as a transmitter or as a receiver. This means 8051 as receiver. Okay, if TI is 1, 8051 is acting as a transmitter. TI 1, clear TI, RETI, end. If not, 8051 is working as a receiver. Put the received value from SBUF into A, from A to port 2, save it at a safe place. Clear the RF flag and return. Okay, this is how you are going to do serial communication programming for serial communication interrupt. Next, we will see what you understand by interrupt priority. Now, what is interrupt priority? Okay, so come here to this slide now. What do you understand by interrupt priority? Okay, whenever 8051 is powered up or whenever 8051 based system is started, okay, a particular priority is assigned to the interrupts. All the interrupts, talking about interrupt priority. Now, what do you mean by interrupt priority? Now, 8051 is connected with different hardware pins. It is receiving signal. Okay, we know how an interrupt works. Now, assume a situation wherein multiple devices have given this signal to the microcontroller at the same time. So, at the same time, multiple devices have given a signal. So, what does microcontroller do? Microcontroller has to serve each of the devices. But how will the microcontroller decide which device to be served first, which device to be served second, and so on? So there is a priority encoder inside the 8051 which will assign priority to the interrupts. I am talking about only the 5 interrupts excluding reset. Reset has got highest priority. So the 8051 system assigns priority like this. The highest priority is given to INT 0. INT 0, that is external interrupt 0. The external interrupt 0 is given the highest priority. Okay. Followed by TF0, that is timer 0 interrupt. So timer 0 interrupt is given the next priority. Then INT 1, external interrupt 1, timer interrupt 1, TF1. Last priority is given to the serial communication interrupt. So the serial communication interrupt is given the last priority by the system upon reset. That means the lowest priority is given to Ri plus Ti and the highest priority is given to INT 0. This is decided upon reset. Now, if the programmer wants to alter this priority, the programmer can alter this priority by configuring a register called as interrupt priority register. So we have a special function register called as the IP register, which is bit addressable. 8-bit bit addressable register. The programmer can assign priority on its own basis. This is the format of IP register. Let us draw the format of IP register. First 2 bits are not there. Then PT2, PS, okay, PT1, PX1, PT0 and PX0. Doesn't it look similar, students? Yes, the format is almost similar to interrupt enable register. There was ET2, ES, EX0, ET0. Here there is PT2, PS, PX1, PT1 and so on. So P stands for priority. Okay, so if we put 1 in any of the bits, that particular interrupt is assigned high priority. Assigned high priority to that interrupt. If we put any bit as 0, then the interrupt is assigned with low priority. Okay, so though we know that Ri plus Ti, that is serial communication interrupt, for example, is given the lowest priority. But if suppose the PS bit, okay, if the PS bit in the IP register is made 1, okay, and suppose there is a signal coming from the other sources also, okay, then there is a signal from timer 1 also, but because we have made the PS bit 1, okay, and PT1 0, that means PS, that is serial communication interrupt, will be given a higher priority as compared to timer 1 interrupt. So the programmer can alter the priorities of the interrupts by configuring the respective bit in the PT register, in the priority register to 1. Now if multiple bits are 1, let us assume a situation in the IP register. Okay, in the IP register, suppose multiple bits are 1. Serial communication 1, this one, these are 0. So here we find that 3 out of the remaining bits are 1. So then what will happen? How will the system come to know now how to assign the priority? Out of these 3, this is serial communication interrupt, Ri plus Ti. This one is PT1. This one is PX1. So if these 3 bits are 1, then what will happen? The 8051 will again get confused. So how will it resolve the priority now? It will check the default table. In the default table, out of these 3, which has the highest priority? That is this interrupt INT 1. So this will be served first, this will be served first, this will be served second, and this will be served last. Okay. So IP register can be used to assign a high priority to any of the low priority interrupts. Okay, by configuring that particular bit of IP register to 1. Okay, but if more than 1 bits of IP register are 1, then in that case what will happen? 8051 will refer the standard table that we have already drawn here. Out of those multiple ones, according to the table, 8051 will then assign priority, final priority, and serve the interrupts in that manner. Okay, this is interrupt priority. Now, small concept is remaining called as interrupt inside interrupt. Now, let us see what is this. Interrupt inside interrupt. What do you understand by interrupt inside interrupt? Suppose a low priority ISR is under execution. A low priority ISR is under execution. That is, such a particular interrupt has given a signal to the microcontroller which has a low priority. Okay, its service routine is being served. In between, suppose a high priority interrupt gives a signal. High priority interrupt has given a signal. Okay, gives signal to the microcontroller. When this signal is received, the low priority interrupt ISR is not over yet. Okay, but still another device which is at a high priority has given a signal to the microcontroller. So what will the microcontroller do? Because this interrupt has more priority as compared to the current one, the current ISR will also be now kept in a hold state. Microcontroller will branch from this ISR to this high priority ISR, serve that high priority interrupt, come back, serve the low priority interrupt, and then come back to the main program. So an interrupt is invoked inside an interrupt. Okay, this is possible if and only if a high priority interrupt request comes when a low priority ISR is being executed. So have you understood the concept of interrupt inside interrupt? This is called as interrupt inside interrupt. Okay, with this we have finished with the basics of interrupts, and now we have done programming in assembly. In the next part we will do programming in C. Okay, the topic on interrupts is interrupt programming in C. So far we have done interrupt programming in assembly language. Okay, so the 8051 compiler has an extensive support for the interrupts, and it assigns, however, it assigns a number to each of the interrupts. It is going to assign a number to each of the interrupts. Okay, it can also assign a register bank to an ISR also. Okay, so it stores. This avoids overhead due to the interrupt pushes and pops, and stores them in R0 to R7 registers. Now see what is the name given. Okay, external interrupt 0. External interrupt 0 is whose name is int0. Okay, is given the number as 0. External timer interrupt 1 is interrupt 0 is given number 1. External interrupt 1 is given number 2. Timer interrupt 1 is given number 3. Serial communication is given in number 4. Now how are we going to write the program? Okay, simple C programs we will see on the slide directly. Okay, which will give you an idea about how to write down this program for interrupts in C. This is the first example that we are going to focus on. Okay, now what is the example talking about? Write a C program that continuously gets a data from port 1 and sends it to port 2. Okay, so that continuously gets a single bit of data from P1.7 and sends it to P1.0. So one bit of data is sent from 1.7 to 1.0. First task. Second task, while simultaneously generating a square wave of 200 microsecond period on P2.5. So we have to use what? Timer interrupt over here. Which timer interrupt? Timer interrupt 0. Okay, use timer interrupt 0 to create a square wave. Assume the crystal frequency. So we are going to do all the calculations first, like we did in the assembly language program we had done earlier. So timer 0 is used in mode 2. It is mentioned that use mode 2. Okay, so accordingly we calculate the value of the count, which comes as 164 or A4H. Now C programming, first step, include the library file. Hash include reg51.h. Okay, then we will be requiring a variable to take the data from P1.7 and put it to P1.0. Both of them are single bit variables. Declare them with the data type S bit. So S bit SW, that is the name of the variable, equal to P1.7. S bit IND equal to P1.0. Okay, one more variable is declared for, we want to generate a square wave. At which pin? We have to generate a square wave at P2.5. So P2.5 is also assigned a value to a variable. So that variable is given the name as wave. Now observe this. This is how the subprogram is to be written. Okay, or the function is to be written in C. Void timer 0 void interrupt 1. From where has this interrupt 1 come? This interrupt 1 has come from the previous case over here. Timer 0 is given the number 1. From this we have come to this name. Void timer 0 void interrupt 1. If it would have been serial communication interrupt, you would have given 4. Okay. What you have to do? Toggle the bit. So which bit? P2.5. This is assigned to a variable named wave. So wave is equal to complemented value of wave. X equal to complemented value of x we used to do. Now the name is given as wave. That's it. That is the name of the variable. You can choose any name, whatever you want. And what is to be done in the main program? In the main program, first take the value from P1.7. P1.7 is given the name SW. So define P1.7 as input by giving SW equal to 1. Configure tmod 0 cross 02 timer 0 mode 2. Okay, TH count we have already calculated A4. IE has to be configured here. IE is not drawn over here. We know how to configure IE by now. So IE will have the value 82 for timer 0. Okay, and then starting the timer we have to do. While 1, what we'll do in while 1? Okay, what we have to do here, there is one statement that is missing, that is start the timer. So you'll also give TR1 equal to TR0 equal to 1. After that you will give while 1. So when the timer is started, the upcounting starts. Okay, whenever the timer overflows, then the control goes from the main function to the timer function, timer interrupt function. Till that time, will the microcontroller remain idle? No. The microcontroller will send the value of SW, that is P1.7, to P1.0, that is IND. So IND is equal to SW. This is what you are going to do in the main function. End the main loop, end the while loop. Okay, this is one classic example in which we have done two functions. Okay, generating a square wave and sending information from one port pin to another. I hope you have understood this. Let's go to the next one. Here, what is given? Again, two tasks are to be done. Okay, write a C program using interrupts. It is specifically mentioned, okay, to do the following. First, generate a 10 kHz frequency wave on P2.1 using timer 0, 8-bit auto reload. Second, use timer 1 as an event counter and count 1 Hz pulses and display them on port 0. Okay, so two tasks are to be done here also. One, timer is used as a timer. Second case, timer is used as a counter. Okay, so two tasks over here. So here there are two timers that are used simultaneously. So see over here, include the header file. 2.1, P2.1 square wave has to be generated. So P2.1 value given to a variable named wave. Okay, one timer will be used as a counter. So I will require a variable. I use the data type as unsigned character count. Now void timer 0 interrupt 1. Timer 0 interrupt is 1. Same thing we are doing. Wave is equal to complemented value of wave. Void timer 1 interrupt 3. Why we have given interrupt 3? Timer 1. Timer 1 is given the number 3. What we have to do here? Count is, it is acting as a counter. So increment the counter and store the count value in port 0. This is what is supposed to be done over here. It is given. Okay. Then what is to be done in the main program? Assign the count value as 0 first. Tmod now you have to configure carefully. Both the timers, timer 1 as well as timer 0 are used. Accordingly configure tmod. It comes to 42. Okay. TH, put the value in TH. You can assign a negative value. We have already discussed in the timer classes. You can assign a negative value. configure IE so that timer 0 and timer 1 both are in enabled condition and EA is also in enabled condition. So this becomes 86. Start the timer and give a while 1 here. Start the timer and give a while 1. This is one more classic example. Many more are there in the book. You can go through the remaining, okay? We'll quickly do this last one. 3 things to be done here. C program using interrupts to do the following 3 things. Receive data serially. Serial communication interrupt is required. Read port 1, transmit data serially and give a copy to port 2. Main function. Then use timer 0 to generate a square wave of 5 kHz frequency on P0.1. 3 things to be done. Data from port 1 to port 2 and serial communication port. 8051 as a receiver as well as timer 0 square wave generation. This much we have to do. So include the header file P0.1. Okay. We have to generate a square wave on P0.1. Assign its value to a variable named wave. Okay. In this function, void timer 0 interrupt 1 number 1. Okay. What we are doing? Wave equal to complemented value of wave. That much we have to do only in the timer function. Serial function, what we have to do? Interrupt number 4. If transmit interrupt flag is equal to 1, that is Ti is 1, then make Ti 0. Else means what? Timer is 8051 is used as a receiver now. So the received byte is present in SBUF. Put SBUF value to port 0 and receive interrupt flag you can make 0. These are the 2 functions. And in the main, the same thing, define port 1 as input, configure tmod, configure th, configure scon. Okay. We have to configure th1 and th0 both. Th1 for baud rate, th0 for generating a square wave. Okay. So both of them are to be configured. Tmod also has to be configured accordingly. Configured IE, start the timer. Both the timers you have to start. Timer 1 as well as timer 0. And what you have to do till both of them are not executed, take the value from port 1, put it into X, send a copy of X to SBUF, also send a copy to port 2. This is what you are going to do in the programming. Okay. So do more practice of this. If you have any doubts or any queries, you can discuss it on our official WhatsApp group or you can do a telephonic conversation with me directly. With this, we come to the end of interrupts. Okay.